Hello, my name is Nikola Marincic. Welcome to another class of our course, An Introduction to Machine Intelligence for Architects and Other Non-Engineers. We are currently in the week number 9. So last time we learned how to implement this particular neural network by using linear algebra. We learned how to represent the layers of the neural networks, including weights and biases, by using matrices and vectors, and we learned how by using linear algebra operations such as dot product and matrix product, we can actually implement the forward pass, cost function, and the backward pass. However, what we still did not succeed to do is to implement a fully working algorithm which implements this particular network. So this is what we will start doing today. We are currently in the exercise number 12, which is about building a neural network using matrices, this time implementing the whole algorithm. So let's start by initializing our NumPy and Matplotlib libraries. And then we have a data set and we have labels. We have a function plot data which plots the labels like last times. And if we use this function on our data set, we see something different now. As you can see, you have actually 3 classes of points here. And if you want to make sure that this is correct, let's look at the labels. So we have points which are now labeled with numbers 1, 2, and 3. Because of that, to each number corresponds a certain color in this dataset. For example, the first point has label 1. This would be a blue point. The second point has the label 2, which is associated with a green point. And points with the number 3 are associated with yellow points. Okay, something new to think about. How should we implement this? Let's do a couple of exercises first. Our first task is about data normalization and label conversion. What do I mean by data normalization? So what we did so far is we implemented a neural network that learns from the data. So we have our weights and biases that we updated by using calculus, by using the gradient descent, computing the partial derivatives in terms of all the weights and biases. And then these weights and biases would change in a way that would enforce our network to get closer to the labels. So we have a data point which is red. We want our neural network to output the value which corresponds to a red point. And then we said what cannot change in this case is the data. So data needs to be constant. It needs to remain untouched. But this is not 100% true. In fact, we can change the data as long as the interrelationships between all the data points belonging to various dimensions remain intact. So as long as the relations between the data points are intact, we can change the data. And why would we want to do that? Well, let me show you what's the problem. So here we have our data points, and in the x direction, they vary from the value of -1 to +4. And in the y direction, they go from -2,2 up to +2. So they are centered around the value, which is around 1.5 in the x direction and a little bit less than 0 in the y direction. When we work with data, you can expect that some of your data points will have very large values. For example, some dimension could be described with a value of 100,000 or 1,000, and then some other dimension could have values which are in the range, for example, from 0 to 1, or some other would be from -15 to +25. So this is not ideal here, because we want all of our data to be centered around the value 0 and then go in each dimensions a little bit towards the negative values and a little bit towards the positive value. This is called data normalization. And for a neural network, it will be much easier to work with such a defined data set. So how can we actually center our data, and how can we make sure that our spread is also something reasonable? For example, that it doesn't go too high or too low in any dimension, but that the relationships between the data points still remain intact. So let's see how we can do. So the first task is to compute the mean, or the average value, of all the values in the dataset. What does a mean mean? Well, we have here a couple of numbers, and if we all added these numbers together and divided them by the number of data points, we will get what is called an average value. So an average value of this whole data set, an average value from a set of numbers. So how can we compute this? Well, there is a function in NumPy called mean. So I can take my data set and type dot mean. And this will give me that the average point within this dataset is around 0,715. Okay. So the next task is to compute the standard deviation, or the average distance from the mean of all the values in the dataset. So this is the mean, this value is 0,715, and we want to find on average how distant all the other points are from this particular value of the mean. So how can we do this? Well, we can type data.std, and this will tell us that the standard deviation of this dataset of all the numbers is 1,657. So if you take an average point and ask how distant this point is from this mean, which is 0,715, the average distance will be 1,657. Of course, each individual point has a different distance from this mean, but on average, all of the data points are 1,657 away from it. But this is not very useful, because what we know here is that these, in the first column here, we have our x coordinates, and in the second column we have y coordinates. And x and y coordinates, they're completely independent from each other. Yeah, one goes in one direction, one goes in the other direction. They're kind of in orthogonal axes, so you cannot mix dimensions. Therefore, we should not be looking for the average of all the data points. That's not very useful. What we want to have is we want to have the mean value of all the x's and the mean value of all the y's. But how can we achieve this? Well, actually, that is not very difficult to achieve. We can just type data.mean and type the following: axis equals to 0. 0 axis means that the first direction goes from top to bottom, or this is the data point axis. So each new value on this axis is a new data point. This is what this means. So if I type data mean axis equals 0, I get now two averages. This is the value which is the average x coordinate, and this is the average y coordinate. As you can see, average x is around 1,5, and the average y is actually a negative value, close to 0. Okay, can we do the same for the standard deviation? Well, of course, we can just take the same formula, so data.std, and this time type axis equals 0. And we will get two standard deviations. Standard deviation in the x direction, so the average distance from the mean, this mean, and the average distance from this mean. Yeah? And now it says normalize the data. Oh, now it gives us actually the instruction how do we normalize the data. Normalize the data by subtracting the respective mean from each data point's components. It means that each data point we should subtract. For example, if it's an x point, we should subtract this value. If it's a y point, we should subtract this value. Yeah? And then dividing each data point's coordinate by its respective standard deviation value. Okay, let me show you what does this mean. So we have data, and we have data mean. If we subtract data mean of the axis 0 from this, what we get? We get that from all of the data points, we now subtracted the respective value. So in this column, we subtracted this value, and in this column, we subtracted this value. And now we need to divide all of the data points by the respective standard deviation value. So for the first column, we need to divide all the values by this value, and in the y direction, we need to divide all the values by this value. So how can we do this? We can just say divide by, actually we need to put this in parentheses first, because the order of operations is such that division comes before subtraction, so we need to make sure to put this into parentheses. And now divide this by data standard deviation of the axis equals 0. And we get the data set, which has the same number of points as this one, but the values are completely different. And we might be a little bit confused about this, because how do we know that this makes any sense? So let's overwrite the old value of the data with this new value. Let's see if this actually makes sense. So plot the normalized data set and compare it with the original one. What has changed? So plot data, and then we put data and labels. As you can see, the data set plot looks almost the same as before. it has the same relations preserved within the corresponding dimensions. But what has changed? Well, what has changed is that now the whole data set is centered around the 0. Yeah? So the 0 is now at the center of this data set. And then you see that all the values around are at most 1,5 away from this value. Or you have some outliers in the y direction which go above 1,5, but they are all kind of in a reasonable range that we can work at. And machine learning usually performs better when our data is standardized in this way. And this is called data normalization. Okay, let's continue. The next task is to implement a function convert label x, which converts a given label x into a vector. The vector has as many components as there are labels. Each of vector's components maps to one of the existing labels and encodes the probability that the label x is of its kind. What does this mean, this complicated sentence? So in our dataset we have three classes of labels. We have labels 1, 2, and 3, but that could also be yellow, green, and blue. So it is not important what number stands for the label. It's just important that these numbers are different, which means they encode different things, different characteristics. Yeah. In this case, our characteristics are that these points have different color. Our labels have three possible values, 1, 2, and 3. And because of that, it is very much advantageous to tune our neural network's architecture to be able to work with, for example, three classes of labels. So how can we do that? Well, we can make sure that our neural network's output layer has, for example, 3 neurons. And each neuron will be expressing a probability for each label. For example, neuron 1 will be expressing the probability that the label is 1. The neuron 2 will be expressing the probability that the label is 2. And the neuron 3 will be expressing the probability that the label is 3. And then when you look at these 3 neurons, we can put them in a vector, which means that we get a vector having 3 components. And for our data points, one of these components will always be equal to 1, while the others will be equal to 0. So we practically get 3 unit vectors for our 3 outputs. And if we want our data point, for example, to be blue, we will force it to go to 1 unit vector. If we want it to be red, we will practically force it to go to the 2nd unit vector. And if we want it to be red, we will force it to go to the 3rd unit vector. So let's do that. So convert label x. So what we will do, so we will make a column vector containing only zeros. So how can we do that? Well, I can type np.zeros and I can put in parentheses the value 3, 1, and then you get a vector which has only zeros. Okay, this is useful. I will use this. I will name this VEC vector. Yeah. And I will put it in my function. And now our labels are 1, 2, or 3. So I can make use of this naming to actually encode these vectors. So what I can say is that vector, so if the input of this function is 1, we want our vector's first component to be equal to 1 and all the others remain 0. If the input is 2, we want our second component to be 1 and all the others 0. And if this input is labeled 3, we want our third component of this vector to become 1 and others to be 0. So we already created a 0 vector. We just need to say, and if we say vector of x, which means this particular index of this vector. So if it is 1, then this should be 1. If it's 2, this should be 2. And if the input is 3, this should be 3 is equal to 1. But the problem is our labels are 1, 2, and 3, and our indexing starts from 0. So the 0 will be the first component, 1 will be the second component, and 2 will be the third component. So we need to subtract 1 from this, and then we need to return this vector. Return vector VEC. And now let's test this. Test the previously defined function on the number of vectors. So convert label, if we set 1, we get a vector whose first value is 1 and all the others 0, and it should work in the same way if we type 2 or 3. Okay, this works. It says now interpret the result in terms of the mapping of the input to the vectorial output. Well, I already told you, these vectors are actually unit vectors. So this is k hat, this is j hat, and this is I hat. So we have 3 unit vectors which have the length 1, and to each of these unit vectors correspond one label. So we want, when our point is, for example, yellow, to map to this unit vector. If the point is blue, we want to map to this one, and if the point is green, we want to map to this one. And why would they be unit vectors? Why should we map them to unit vectors? Well, first of all, because we can interpret this nicely in terms of probabilities. So the first component encodes the probability of the first label, second component encodes the probability of the second label, and third component encodes the probability of the third label. So if the value of one of the components of our vector is equal to 1, this means there is a 100% probability that this vector is representing this label. But also we know that our unit vectors, I hat, j hat, and k hat, are linearly independent vectors. This means that you cannot represent k with a linear combination of I and j, and all the other combinations are also impossible to represent in terms of the other two vectors. So because they are completely independent from each other, they're a good structure to encode 3 different classes that are also completely different from each other. Okay, so this will be the interpretation. Of course, I will not type it here. Now it says implement the function sigmoid that takes the vector input. So we already did this before. So sigmoid of x, we should return 1 divided by, in parentheses, 1 plus exponential function of negative x. Now let's test this function. So sigmoid of 0, this should give us the value 0.5, so this means that it's correctly defined. Before we start implementing our neural network, let's take a look at the task number 2, which is about learning some other useful NumPy functions for manipulating data. So xvec is a given 5-dimensional vector. So this is actually a column vector with 5 dimensions. The task is to transform this vector so that each of its components, so these numbers, gets rounded to either 0 or 1, depending to which one it is closer. So if it's 0.4, if we round it, this should be rounded to 0 because it's less than 0.5. This one is greater than 0.5, so it should be rounded to positive 1. So how can we do this? Well, there is a function in NumPy called rint, so mprint, and if we just plug this vector in it, so xvec, we will get exactly that. So the first value is smaller than 0,5, so it's 0, second one is 1, third one is 1, and so on. So this was very easy. Let's look at another example. So xvec2 is a given 10-dimensional row vector. So this is a vector which has 10 columns and 1 row. It says return the index of the maximum value within this vector. So for that, let's maybe change the values a little bit. Let's make them from 0 to 50. All right, so we have now different values here from 0 to 50. And what would be the index that contains the maximum value within this vector? So let's see what's the maximum value here. What's the largest number? 41, 47 looks like it's the largest number. And what is the index within this array? So this is the first element, second, so 0th, first, second, third, fourth, and fifth. So the 5 should be the index of the highest element. So how can we return this index number 5? So there's a function in NumPy called argmax. And if we plug here xvec2, it will tell us, yes, 5 is the index which contains the maximum element within this range. Yeah. Of course, you can assume that argmin will give you the smallest element, which is index number 4, 0, 1, 2, 3, 4, which is number 8. Okay, argmax and argmin. Very useful function. And now our task 3 is to actually implement our neural network. So we have our equations from the last class that we learned how to work with. We have the forward pass, we have the cost, and we have the backward pass. So we need to implement a 2 times 5 times 3 neural network using only vectors and training to classify between 3 groups of points associated with different labels. So let's start making an algorithm. what we know that we need is we need the length of our data. So I will just type this as data length equals to length of our data. So we have 13 data points. Okay, that is fine. So what we can do next is pick a random data point from our dataset. We did this before, so how can we do this? So we have function np.random.randint, and we plug as an argument data length, which is the length of our data. And this is guaranteed to give us a number between 0 and 13, yeah? A valid index with which we can then take a data point and a label from our dataset. So we will call this index. Yeah, and let's place it here. Let's now implement looping, so epochs. So for epoch in range 1, we will first do a loop which contains only one epoch, and then it's just easy to put values, larger values in it, to repeat it more times. So far this is okay. Then what would be a data point? So d point would be data of this index, and let's plot it. So we get our row vector, and we need to convert this point actually into a column vector. So we should do reshape in the form 2, 1, and now we have the column vector. What else do we need? Well, we need our label, so we will call this variable y, and we will take labels of the same index. Yeah, and let's print the label. So the label is still 1, 2, 3, so we need to convert it. So convert label, and now we have a column vector represented as a label. Okay, that's fine. So now to go further, we need to compute the forward pass, but before that we need to instantiate our weights and biases. So let's do that first. What do we have here? Our architecture of the neural network is that it actually has 2 neurons in the input layer, which makes sense because these are x and y coordinates. These are data points. In the second layer it has 5 neurons, which means it has to have 5 biases in this layer. And in the output layer it has 3 neurons, which is great because our data points have 3 labels associated with them, and then we can take that each output is associated with one of these labels. Yeah? But how many biases and weights should we have? Well, the second layer has 5 neurons, which means it will have 5 biases. So let's instantiate that. So biases of the layer 2 are np random rand n, and we'll have 5, 1 here. Weights of the second layer, well, random rand n. We know that layer 2 has 5 neurons, and the layer before it has 2 neurons, so we need a shape 5, 2. So 5, 2, and then biases in the layer 3 will have np random rand n. What do we have here? We have 3 neurons, therefore we need 3 biases, 3, 1. And for the weights of the layer 3, we need 3 neurons, and these 3 neurons are multiplying 5 outputs from the previous layer, so the shape should be 3, 5. Okay, this is fine. We also need somewhere to store our partial derivatives in terms of all of these weights and biases. So how can we do this? So if I type b2 now, I get that it has 5 biases, and if I type shape, this gives me the shape 5, 1. So our partial derivatives in terms of biases should be in a data structure of the exactly same size. So let's define that. So db2, dw2, db3, and dw3. Well, db2 should be storing only zeros at the beginning before we put any concrete values in it. So db2 is going to be equal to np zeros, and instead of the shape we can type b2.shape. Then weights should be np zeros w2 shape. So I can now copy and paste further. This should be biases of the layer 3, and this should be weights of the layer 3. Now we have all the necessary data structures. So what do we do next? We have our data point and we have our label. So we need to compute the forward pass. So we can say that the activation of the first layer is actually our data point, yeah? And now, to compute the activation of the second layer, what do we need to do? Well, we need to compute a sigmoid of a dot product between weights of the layer 2 and activations of the layer 1 and add to it biases of the layer 2. And for the activations of the layer 3, we just need sigmoid of the dot product of the weights of the layer 3 and activations of the layer 2 and adds to it biases of the layer 3. Okay, this is fine. Let's see the activations. We have the 3 activations that we need, and we can associate, most importantly, these activations with our actual labels. So this should be our forward pass here. All right. Now we need to compute the cost or loss. What would be the cost or loss? Well, cost will be here activation of the last layer minus the labels, yeah? And we need to square this cost because we are interested in the mean squared error. We can type it like this. This is the squaring. And then we need to sum these values, yeah? NP sum. And then we have the cost for this particular data sample. As you can see here, this will not be a total cost because total cost is defined for a whole epoch, and the epoch is defined when we go through all of the data points once. But we are here implementing online training first, so total cost will not mean what it usually means. It will just be a cost for a single data example because we are going data example by data example here. So we can then plot this cost, and the cost is 1,62888. Okay, let's now compute the backward pass. So first, we need to compute the partial derivatives in terms of the cost. I will call this dc, and dc will be equal to what? 2 times a3 minus y. So last layer of activations minus labels. Okay, now what do we need? We need partial derivatives in terms of the weighted sums of the last layer, which is layer 3. We will call this delta 3. And delta 3 will be dc, which is partial derivative of the total cost in terms of our outputs, and then times, by means of a Hadamard product, activations of the layer 3 times 1 minus activations of the layer 3. This is just the derivative in terms of the sigmoid function. So a3 times 1 minus a3. So delta 3, it has 3 outputs. This is fine. Okay, let's now compute the partial derivatives in terms of the weighted sums of the layer 2, so delta 2. So I already know how to do this, but if you're wondering, let's just go back to our formula here. So to compute the partial derivatives in terms of the weighted sums of any layer, so this is of the following layer, and this here is of the any layer, we just need to multiply the activation of this layer times 1 minus the activation of this layer, and then do a Hadamard product with a dot product of the transposed weights of the layer above with the partial derivatives of the weighted sums of the layer above. So how do we do this? So it's going to be equal to a2 times 1 minus a2 times dot product weights of the layer 3 transposed with the delta 3. Okay, now that we have delta 2 and delta 3, which are partial derivatives in terms of the weighted sums, it is easy to compute partial derivatives in terms of the weights and biases. It is especially easy to do this with biases, so db3 is equal to delta 3, and db2 is equal to delta 2. Okay, how do we do it in terms of weights? Again, let's look at the formula here. So for a given layer L, we just need to compute a dot product of the partial derivatives in terms of the weighted sums of that same layer and the activations of the previous layer transposed. So dW3 is going to be equal to the dot product of the delta 3 and the activations of the layer before it, which is 2, transposed. And the weights, derivatives of the weights of this layer 2 is just going to be equal to mp dot delta 2 and activations of the layer 1 dot t. Let's check if this works. So dw2 should be the same shape as w2. Okay, if they are the same shape, we can subtract one from another to minimize the loss. So how do we do that? Well, we have the variable, or we do not have the variable. Let's put a variable step size here. So step size equals to, for example, 0,5. And now what we want to do is we want to update weights and biases. How do we update them? Well, we have biases of the layer 2, and we need to subtract from them derivative of the biases of the layer 2 times step size. And we need to do this for biases of the layer 3, yeah, dB3 times step size. We need to do this for the weights of the layer 2, and we need to do this for the weights of the layer 3. So W3 weights of the layer 3 times the step size. And this should be it. Okay. When we run it once, we do not have any errors, so that's promising. If we run it 10 times, something is happening, but how do we actually evaluate what is happening? If we plot the total cost, this will not give us results that we expect, because our total cost is not according to the one loop through all the data points, but is the cost of a single data example. So if we wanted to plot each, for example, 10 or 20 iterations, cost of an individual example, what do we get? So if epoch modulo 10 is equal to 0, I will explain later what this expression here means, then let's print cost, which is going to be equal to C here. So cost is 0,2934, okay? And now let's do this, for example, 100 times. So this is not as clear as total cost, as you can see. This is now cost of a single data example. This is a cost of a single data example. So all of these are the cost of a single data example. But if we want to know if this is actually running well or not, we should just run a lot of iterations and then see if numbers in general go lower or not. Yeah, this is not a total cost, but still, if this number is sufficiently smaller than the first one, it means we are on the right track. But as you can see, this is not a good way of working. How can we improve this? Well, to improve this, we need to create a function which will evaluate how many data points are correctly recognized. So let's call this function evaluate accuracy. Okay, what will this function do? Well, this function now needs to go through all of our data points and then compute the forward pass with our current weights and biases and see whether the prediction matches the actual label. So how do we do that? Well, we have our data and our labels, so we can make a zip of our data and labels. So zip data and labels. And then we can say for D, L, D is a single data point, L is a single label. In this zip, we can print D, L. Nothing happens because I did not run this function yet. So evaluate accuracy. As you can see now, each data point has some x and y values and has a label. But these are the old way of representing labels and data points. We need to reshape them, yeah? So we have our D point, or let's call it activation of the layer 1, is just going to be equal to D reshaped into a column vector with 2 rows and 1 column. And Y, which is the label, should be also converted, so convert L. And now we can print A1, then we can have an empty row, and then print Y and have another empty row. Let's just see what's going to happen. Okay, now we have our first data point represented as a column vector, then its label represented as a column vector and converted, and so we have this for each of these data points. We can maybe do this if it's not clear to you what's actually going on. So first data point, second one, third one, fourth one, until we loop through all of these data points, yeah? What are we interested in? We are interested to compute the final activation. This is only the data point. We need to compute the final activation. So we need to compute the whole forward pass. How do we do this? Well, it's easy. We can just copy and paste these lines. So to compute the activation of the second layer, we just do a sigmoid of this dot product and add B of the second layer. And to compute the activation of the third layer, we do the same thing. We apply the same formula, just update the index by value 1. So we can now print A3 and Y, yeah? So what's going on here? We have now the output of our neural network. This is this vector, and this is what it should actually output for this value. When it sees this value, it should output this, yeah? But what we said about probability is, if this value is larger than 0.5, then this means this is a correct prediction, because this prediction is greater than 0.5. If this value is smaller than 0.5, then this is the negative prediction for the second value. So we practically want to now round these numbers. If they're larger than 0.5, we want to round them to 1. If they're smaller than 0.5, we need to round them to 0. And then we will compare them with the actual labels. So what do we do? Well, we can say the following. We can say prediction is equal to MPRInt, this is to actually round them, of this last activation. So we can now plot the prediction and plot the actual label. And now we just need to see if these things are matching, yeah? So if we are interested to see if two numbers are matching, I can ask if A, for example, if 5 is equal to 3, and I will get that this is false. If 5 is equal to 5, it is equal to true. But I cannot do this with arrays, NumPy arrays. They have a different way of asking whether they are equal. How can we do this? Well, we can do the following. We can say if, and then there's a command in NumPy called mp.array equal, and then we put as arguments arrays that we want to compare. So if we want to compare our actual label, which is y, and prediction, if this is true, yeah, then we want to print correct prediction. If not, else we want to print false prediction. Oops. Or incorrect prediction. And then we can remove these lines. So you can see I got actually 100% correct prediction here. Let's make less of these steps here. Let's make 100. Now I have some incorrect predictions too, yeah? But this is not good enough. I want to know how correct or incorrect prediction is. So I need to keep track of how many correct predictions there are for the whole data set. And then I will divide this number with the number of elements in the data set to actually obtain the accuracy. So num correct, we will start with 0. We have 0 correct in the beginning. And then as we find a correct prediction, we will just increment this number by 1. So num correct plus equals 1. And if not, well, nothing. We do not have to care. And now we need to return what? We need to return num correct number of correct answers divided by how many data points there are. So data length, if I'm not mistaken. So data length. And now we get a number 0,6153, which means there is 61,53 accuracy of our neural network when it classifies our data set. Okay, let's plug this function within our neural network. So if epoch is divided by 100, evaluate accuracy and store this accuracy in ACC. Yeah. And then let's print this accuracy. As you can see, if we do it every 10 steps, we get this accuracy, but I don't like these huge numbers. So how can I change this? I can actually round this number and multiply them first by 100. Yeah, so accuracy is equal to accuracy times 100. This will take the old accuracy and multiply it by 100. Now we get percentages, but now we want to round them to, for example, 4 decimal points. So I can just say MP round this whole thing to 4 decimal points. Yeah. And now I can say print accuracy is equal to ACC %. And now you see accuracy starts by 22% and goes to 60 and then to 50. Okay, now let's see how many steps do we actually need to make here. Or maybe I should make a larger step size here. Maybe this helps, but in principle what I need to do, I need more iterations. So let's put 1000 iterations and I will check every 100 iterations to plot this. So let's do 1001. With 1001 iterations, I get to 76% accuracy. So we need more. Let's do 1500. And with 1500, we have 100% accuracy. Okay. But now I promise you that I will show you what does this thing here mean. This epoch divided by 100 equals to 0. Well, this thing here is called a modulo operator. What does modulo operator means? So if I wanted to divide, for example, 5 divided by 2, this is of course equal to 2,5. But what if I wanted to have this represented in terms of natural numbers? So if I divide 5 by 2 and I cannot use decimal numbers, I can do this operation here, 5 divided by 2, and I get 2. So 5 divided by 2 with this way is equal to 2. What does this mean? Well, it means that 2 goes only 2 times into 5. So 2 times 2 is 4, and then there is a remainder 1 to this operation. And how do we get this remainder? Well, we get it with this modulo operator. So I can type 5 modulo 2, and I get the remaining modulo 1. So if I wanted to divide, for example, 7 by 2, we know that this is going to be equal to 3. So 3 times 2 is going to be equal to 6. And again, modulo, the remainder will be equal to 1. Yeah. But if I divide, for example, 4 by 2, this will just be equal to 2. So the modulo in this case will be equal to 0. And I can use this property of the modulo to actually do something each number of iterations. So let me show you what I mean by that. So let's make an array of numbers. NP arrange 20 numbers. So now I have a list of 20 numbers here. Now let's make a for loop out of this. So for I in this range, print I. Now I have these 20 numbers printed from 0 to 19. So let's now do print I divided modulo of, for example, 3. So what this will do is divide 0 by 3 and plot the remainder. Divide 1 by 3 and plot the remainder. Divide 2 by 3 and plot the remainder, and it will do it for all these numbers. So as you can see, the remainder will start repeating. So if we divide this by 3, we get 0, 1, 2, 0, 1, 2, 0, 1, 2. If I divide it by 5, I get 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So what can I ask here? I can ask, when is this modulo equal to 0? And as you can see, this modulo is equal to 0 only in a couple of places here. And if I ask, when is this actually equal to 0, this will give me return true or false. So I will get true, I will get then 4 falses, then I will get true, and then again 4 falses, true, and 4 falses. So depending on this number that I divide with, this gives me a certain arrangement of true and falses. So if I put 10, this will give me true each 10 iterations. So I can then use this requirement when this number is equal to 0, do something. So if this condition is true, then do something. And what I'm using it for, when my epoch, which goes from 0 to 1 to 1500, is when it's divided by 100 and gives me the remainder 0, then evaluate accuracy and then print the accuracy. And the effect of this will be that I will just get accuracy printed each 100 loops. And this is what we get. Okay. We also want to visualize this classification because our data point is in 2D, so it would be useful to actually visualize it because this is one of the rare cases where we can actually visualize it. And this is what the task 4 is about. So it says, apply these functions, create mesh grid and plot neural simple to visualize the results of the classification. Add the necessary code to the function plot neural simple where marked. So create mesh grid. We will use this function in the beginning. So I will say grid is equal to create mesh grid of this data. Now let's see what we need to do with the neural simple. Well, we need to give it some parameters, yeah? And the parameters are weights and biases of the layers 2 and 3. So let's just take use of this and put it here. So parameters are going to be all of these weights and biases matrices, okay? And then we will plug them into this function, and when one happens, this is our data point. We see it here. So we can say that this is actually our first activation. And then we simply need to compute the forward pass from this point on. And we already did this in our last step. So I just need to take these 2 lines of code, compute the activations of the second layer, compute the activations of the third layer, and now we should compute the score. So activations of the third layer, let's see what they are. So what do we want to do now with this activation in terms of visualization? Where, as you can see, all of these values represent a probability of this output representing a certain label. So this represents the probability of the label 1, this number represents the probability of the label 2, and this one represents the probability of the label 3. So we are just interested, what is the highest of all of these probability? If the highest probability is represented with a higher number, then we can use the function argmax to tell us what is the argument which has the highest value. So if I type mp.argmax of this output, A3, this will tell me that the argument 1, which is this one here, has the maximum value. So how can we actually instrumentalize this function argmax in terms of visualization? If we visualize our classification, we need to have boundaries between 3 different areas. One accommodating yellow points, second area accommodating blue points, and the third area accommodating green points. So we need to somehow distinguish between these areas, and we usually distinguish them with different shades of gray. But how do we get actually 3 distinct shades? Well, this argmax, when we plug an activation of the last layer to it, it can give us 3 values. Either the first value will be the highest value, and then the output will be 0. If the second value is highest, then the output will be 1, and if the third value is highest, then the output will be 2. And this will actually give us 3 different values, 0, 1, and 2, that we can use to distinguish between 3 different regions of our visualization. So let's do that. So I can just say that score is equal to argmax of this A3, and then I will assign score to this Z, which actually paints each pixel of our visualization. And finally, I need to use this function plot neural simple here. So I will put it here, and what do we need to give to it? We need parameters, which we already defined. We need the grid, which we already computed. Data and labels we have, epoch we have, and accuracy we call it ACC. And now let's just make sure that we do not plot this too many times. So let's do it 1000 times and plot it each 200 iterations. argmax is not defined. Okay, so there's a mistake here. It should be numpy.argmax. Okay, now it should work. As you can see, as our accuracy increases, we can also see it in the visualization, that there are three distinct regions, each encompassing a different classes of points. So this one encompasses yellow ones, this one encompassing green ones, and this one encompassing blue ones. Okay, that's fine. Let's try doing it once more, just for fun. Okay, this seems to work. We have 100% accuracy. And we have completed the task 4. Now we come to the task 5, which says modify the algorithm to implement batch training. Well, first of all, let's for a moment remove the visualization. Let's comment it out. Yeah. And let's do only one epoch. Okay, accuracy is low. So within this epoch, we now need to loop through all of our data points. How do we do this? So we can just do for D, for example, will be our data point, comma, L will be our label, in zip data labels. Yeah. Now what would be our data points here? So D will be a data point, but we will call it data. So this data point here will be a row vector, and we need to make it into a column vector, so we need to reshape it. So what we can do is just say D point is equal to D reshape, and Y would be a convert label, not of our labels given index, but of this L here. Yeah, this is our label from our data set, and then we can get rid of this indexing. This will not work because in this for loop we now need to indent the things which are within the loop. And what things are in the loop? Well, let's put all of them at the moment. Just select them and press tab. All right, now we have a data point, which is D reshape. We have Y, which is our label, which is now converted from this Y. And now we do the forward pass. So A1 will be D point, A2 will be what it is, A3 will be what it is. And now we have a cost loss of a single example, but we need to accumulate this cost for all of the data points. We have, I don't know, 13 data points here. We need to accumulate all of these individual costs into a total cost. Where can we do this? Well, we can do it after instantiating each epoch. So we can say TC, or total cost, is equal to 0. And then when we compute the cost here, we can add it to the total cost. So TC plus equals C. So we now added individual cost to the total cost. That's good. Now we have the backward pass. So we compute the backward pass of weights and biases. But this is not correct now because we need an average weights and biases. Yeah. So we need another data structure which will now be initialized with zeros, but will be of the exactly the same size as the weight matrices and bias matrices, which can actually also add them up, like we are adding here cost of an individual data point to a total cost. We need to add individual biases and weights of a single data point to this variable, which aggregates them. So let's instantiate this variable somewhere. We can copy paste this. We can copy actually here where we instantiate weights, derivatives of weights and biases, and add it after the total cost, because we want to make it equal to 0 after each epoch. Yeah. And we will call it now DDB2, DDW2, DDB3, and DDW3. If you have a better name for this, please use a better name. I do not know what name to use here, so I'm just using DD, like we did before. And this will have exactly the same shape as our biases and weights, which is exactly what we want. Okay, so what do we do then? Now when we computed our weights and biases for all the layers here, we just need to accumulate them within these variables. So how do we do this? Well, DDB2, we will just add to it all the DB2s, yeah, for each data sample. To DDW2, we will just add all the W2s. To DDB3, we'll just add all the DB3s. And to DDW3, we will just add all the DW3s. Okay, here we now have accumulated all the partial derivatives of weights and biases. To get average weights and biases, we need to divide all of these weights and biases by the number of data points. So, but we do not do this in this for loop. This for loop is finished, yeah? We have aggregated everything we need to know, so we need to go one step back. So I will select all of these things and press Shift Tab to go one step back, so to leave this for loop here. So now I need to divide DDB2, divided equal, which means divide by each value by what? By the data length, by the number of data points. And we simply need to do this for all of these matrices. Need to do it for DD weights of the second layer, bias of the third layer, and weights of the third layer. Okay, and now when we update our weights and biases, we do not any longer update them with weights and biases of individual points, but with these average weights and biases, which are represented by variables DDB2, DDB3, DDW2, and DDW3. And now we should have a working algorithm if everything is still fine. And just let me run it. Okay, we run it only once and we get the accuracy. But can we also plot the total cost next to the accuracy? Well, of course, I will say here total cost, and I will say TC. Now you can see accuracy 0%, total cost very, very high. Okay, let's just run this multiple times. Let's run it 100 times and check each 10 times. As you can see now, the total cost is actually going down and the accuracy is increasing, which makes complete sense. If the cost is going down, accuracy is going up. But we need more iterations here. So let's do 500 iterations and check each 50 times to plot. Okay, again, we could be doing better. So let's do 1,500 iterations. Actually, let's do one more. And check each 150 times. As you can see, now we get to 100% accuracy and the total cost is going really low. As you can see, when we go to the total cost being around 0.67, this guarantees us to have 100% accuracy in classification of this dataset. And now we can put back the plotting. We can check it each 300 iterations. Total cost relatively large, 14, but as you can see, very quickly it gets better. And as soon as it gets below 1, we get 100% accuracy. And that's it for this exercise. What we have learned in this exercise is how to implement a neural network algorithm whose number of layers and number of neurons per layer is hard-coded, so we defined it in advance. So we do not yet have a flexible algorithm at hand where we can specify how many layers we want and how many neurons per each layer. And this is what we want to do next. But because this video is getting too long, I will make another one in which I will cover creating a flexible neural network algorithm by using linear algebra. So see you in the next video.